Hello, everyone. Good day and welcome again to our AB 106 class or the properties of AB materials. So this time I will discuss about the aero and hydrodynamic properties of AB materials. So this is a lecture 5 of the course, which is fundamental for the properties of AB materials. Okay, so as I have mentioned, this is already our lecture 5 or lesson number 5 of the course, which is part of the midterm coverage. Uh, After this, we still have one topic, the sixth lecture, to complete the coverage for the midterm examination. Okay, aero and hydrodynamic properties of AB materials is one of the components or fundamental topics of the properties of AB materials because in food process, in post-harvest handling and storage, the air or the from the aero or air and hydro or water are the two important factors that must be considered, particularly on handling, on machine design, on preservation, storage, drying. So these two factors, important factors, must be considered. So when you say hydrodynamic, it's the movement of particles, movement of agricultural and biological materials through the application of air. So there are some equipment, there are some technology that through the application or through the utilization of water, for example, hydraulic, there are hydraulic instruments, hydraulic equipment that are used nowadays to move, okay, to transport the agricultural product from one place to the other place. So as I have to uh, say it again, that the water and air properties are also important in the agricultural and food products. So as I have mentioned, the handling and processing of agricultural and food products, air and water are used as carrier for transport or separation. So if you have observed, there are some factories, there are some industries, particularly on food processing or food preservation, even on the market, there are some transporting equipment that utilizes air and water to transport the agricultural produce from one place to the other place. So it involves power, instrumentation, and control. It involves electrification. It involves mechanical aspect, but especially the application of properties of agricultural materials. So before that particular equipment or instrument has been designed, so it has been considering the properties particular for that material or sample that is being transported. So pneumatic separation and conveying has been used for many years. So when you say pneumatic separation, if you have observed or if you've been to a milling plant, for example, a rice mill, you can see that the rice has been transported or transferred from lower place to the higher place, and then it will be milled particularly through pneumatic separation, through the blowing of air. No, so there are some machine also uses air to uh, to screen out, right? To sieve, to screen out, to crush, and even to process, to dry agricultural products, particularly grains, just to dry the grains using air. So the air is quite somehow heated. No? There are some heated, for example, heated air dryer. So the heated air dryer will dry the grains through the application or through the suction of dried air. Okay, so this is one of the important example or one of the most common example of pneumatic separation. So conveying, for example, at the picture as shown, the apples are being conveyed, right, together with washing. So it is being conveyed from one place to the other place until the process is done, right? So there's disinfection might be, there is not just washing, normal washing, but there's also infection or even a cleaning of the apples. So after that, after washing, it will be segregated. It will be classified according to the size or maybe according to its uh, shape. And then it will be air dried. So what is being applied in the air drying is air or water, okay, heated air. So fluid flow or fluid mechanics are widely applied in handling and processing. So that is why before you can take AB 106 or ABE 106, you are being required to take first heat transfer, or it can be a core requisite with the fluid mechanics, so that uh, all the things that you have learned in the heat transfer, thermodynamics, will be interrelated with this particular course, because the fluid flow or even the fluid mechanics is one of the fundamentals when we study the various properties of AB materials, particularly in the aero and hydrodynamic properties. The knowledge of physical properties which affect the aero and hydrodynamic behavior of AB products becomes necessary. Why? For example, when we design a particular, when we innovate a particular machine or a particular object to transport, to process the agricultural produce. So before you can design that one, you need to consider, you need to review the physical properties of that particular product. Because, for example, your design is to, your aim is to transport particular product to this system or to the other place, and then you did not review or consider its physical properties. What are the common sizes, shapes, volume, and etc. of that particular produce? So might be your design machine will be a inefficient, or it's not suitable for that particular product, because you forgot, or you tend to consider, not to consider its physical and even other physical or even its shall we say, like color properties, chemical properties, and etc. So accordingly, the physical properties is one of the most important properties aside from uh, other properties that must be considered in hydrodynamic and aerodynamic instrumentation. So it is being said that the most affected one is physical. For example, you design this machine and then the hole or the conveyor is not good enough for the sizing or for the grading of that particular produce, so it's not applicable, no. Your design is nonsense, so you must review and consider the basic physical properties of that particular product. Okay, the two important aerodynamic characteristics of a body, okay, are its terminal velocity and aerodynamic or drag coefficient. So when we say terminal velocity, it's from that word velocity. Okay, it's movement according to the rate, okay, per unit of time, and aerodynamic drag or its coefficient, drag coefficient, from its velocity. What are the factors or what are the things that being attributed to its velocity? So that's being considered as drag coefficient. So when we say drag coefficient for particular movement in fluids, drag force is resistance to its motion, right? So for example, when you drop one apple from the like uh, from a building, like a two-story building, you drop an apple from the top of the two-story building, and then it's moving down, right? So the drag is being an attribute of the air or the surrounding. So the weight of the body, okay, is equal to the resisting force from the ground going to the particular body. It's like an opposite, right? In our statics and dynamics of rigid bodies, we say that the opposite force, okay, there's an opposite force on the weight of a particular body, right? So for example, for that particular apple, when you drop the apple, okay, the weight of the apple, that's the force going down. But there's one force that is opposite to the weight of the body, opposite to the weight of the apple, which is equal to the weight of the apple being resisting. So that's there's a factor between that particular force. So the resistance, okay, the force that resists for that particular weight is called a drag. It might be attributed with the environment or particularly the surrounding, like the air, maybe, okay, humidity might be. Drag coefficient is a coefficient related to drag force, okay? So for example, as I have mentioned already, so you can see a diagram, or you can see a picture where it represents the body. For example, the yellow colored, it is, for example, this is the a fully perfect, or it's a perfect shape apple, and then it is being dropped going down, right? So you can see that the weight of the apple, okay, so the weight of the weight of the apple, or the body, okay, is has an equal, or equal resisting force, which is also going up. Okay, so and then the drag force, this one, FD, is being the resistance that makes maybe somehow the apple to move other than going down, straight going down. So the material is, especially if the material is too I mean, it's not heavy, like it's quite uh, shall we say, the weight of the material is less than to the weight of the air, right? So it will be moved other than moving down, directly moving down. So it will move like parallel, or uh, like in agreement with the movement of the air. So FD is the drag force, and then FG is the gravity force, and then FB is the force of the body or the object. Okay, so the drag force is just the force that will uh, I mean, will affect the movement of the material when it is being moved. For example, not just the material being moved going down, but there are some materials, for example, in transport, okay, when you transport, or for example, in a conveyor, right? When you convey a group of banana, or a group of mangoes, so when you convey a group of mangoes, the resistance between the mango and the material that you used, for example, the metal sheet that you used, there is a drag force being shall we say, drag or frictional force that is present. Okay, so earlier, or weeks ago, we have discussed already the frictional forces. So the drag and frictional forces are also quite related. Okay, so when you say drag, it is also a coefficient that will affect the movement of the material being transported or being elevated from one place to the other place. Okay, overall, resistance of fluids act to particle can be described in terms of drag force using drag coefficient. Okay? So, frictional coefficient, sir, it is applicable, sir, kung the acting forces which will affect or will resist the movement of the particular product in like a flat surface. But when we say movement through the air or through the fluid, so it is called drag coefficient. So that's how they differ. Comparing with fluid flow in pipe principle, okay, in your fluid mechanics, okay, in your fluid mechanics, and even in your dynamics, you can relate this topic as well, because in the fluid flow in the pipe, there are also frictional losses that we consider. For example, water, basic one. Okay, if you have a water source and then you have that pipe, okay, from the source, then there's water, pressurized water going to your house or your household. When you open the faucet, when you open the faucet, you tend I mean, you can experience that the faucet will somehow like there's an effect of a blowing effect, like sometimes you will be shocked because of its pressure, high pressure. So when the water flows from the source going to the faucet, there is frictional losses or frictional forces act on it with respect to the pipe. So okay, so it is related in the movement also of the material once it is being moved through the application of water or air, right? Another example, not just for the water, for example, um, you tend to mill, I mean, a corn. Then in the milling of corn, from a lower uh, part of the milling, okay, the corn, the grits will be moved upward. And then move upward, it will be just moved by the air. Okay, the factors or the attributes, the resisting forces, which causes the grains, I mean the corn to go upward due to the force applied in the air or the pneumatic air, are those considered they are considered as uh, coefficient, drag coefficient in dragging the grains going up. So this can be considered as a drag coefficient, and then it will be similar to the frictional coefficient or friction factor. So I already mentioned that the frictional factor or frictional coefficient is similar or related to the drag coefficient. So mostly by practice, we use drag coefficient for uh, uh, a combination of air or somehow humid or water which causes the material to move, right? While frictional is just a material to material, okay? Like a conveyor, as I have mentioned, you convey the mango, okay, through using a conveyor and a flat surface. So assuming that the mango are being conveyed from one place to another. So the that point wherein the mango will not move means that there is frictional forces resisting, which is equal to the weight of the mango, that way it will not be moved even if it is being transported or conveyed. So there are a lot of factors that will be considered. So the main goal of this is that to consider the materials that you need to use when you design a certain machine, when you design when you innovate something in related to the food processing or to the AB products. So that's the main goal. Why we need to consider the factor, or whatever the factor it is, because of the main goal to analyze the relationship between the properties of the materials and the physical aspect, which include aero and hydrodynamic properties. Okay, so how to solve the frictional factor? Okay, what is the equation involved in the frictional factor? So the frictional factor is given as the shear stress, okay, uh, divided by the kinetic energy over the unit volume of flow. Okay, so what flow? Maybe it be a flow of water, or it is a flow of the air. Okay, so where we already learned that kinetic energy is the half of the velocity square. Okay, so if you have the rate, it is in velocity rate, maybe in meters per second or whatever. So uh, you just square that particular unit, and then half of that is the kinetic energy. And then we all know, okay, we already know that uh, the standard or the constant uh, air, the constant, what do you call, for the air, which is 1.25, density of the air is 1.25 kilogram per cubic meter. Okay, so that's the standard. Some will use 1.26, 1.2567, like that. But let's just say 1.25 kilogram per cubic meter. Okay, is that really the standard for air in all aspects? No. The standard density of air might be different with respect to the relative humidity or the temperature of the surrounding. Okay, so for example, that particular surrounding is quite too humid or quite too dry, so the specific density, the density of air changes as well. Okay, so let's just assume that this density is the standard for that particular, like this, I think 30 degrees temperature, and the relative humidity like 60 to 80%. So okay, so this is the formula on how to get the friction factor, and then we can simplify. By simplifying this, we have we have a friction factor of 1/2 of the F density of air times the uh, area, okay, and square square of the velocity. Okay, so 1/2 F density AV square. So this is the final or the simplified formula for getting the friction factor, considering the shear stress and kinetic energy. So, or somehow we can have the force, okay? Force is equal to the 1/2 of the friction factor times density of air times the area of the material times the velocity square. So that's how we get the force re resisting or available on which relate to the fluid flow frictional factor. For general drag coefficient or drag coefficient CD, we can also get using this equation. The drag force per area divided by the kinetic energy over unit volume of flow, where again, we have kinetic energy of 1 half mass times the V square, okay? So 1.25 kilogram per cubic meter is we will consider as the uh, constant air density, okay? So simplifying, we can have a formula or equation for the drag coefficient, the general drag coefficient, which is 1/2 CD or 1/2 drag coefficient times density times the area velocity square. Okay. For flat plate with a laminar boundary layer, the drag coefficient can be computed as well with this formula. CD or the drag coefficient is equal to 1.328 divided by the NR2 or the square root of NR, okay, NR zero point 0.5, okay. So the NR, what is NR by the way? The NR is the Reynolds number, okay. NR is the Reynolds number, which can be computed as well as DV's the length of the plate or the diameter length of the plate or even the sphere times the density of the air divided by the what is this? This is mu. So the mu is like a constant as well, usually given in most problems for getting the uh, Reynolds number. For flat plate with a laminar boundary layer, the drag coefficient can be computed as CD is equal to 4.55 divided by the log of Reynolds number up to 2.58. Okay. So for flat plate with transition region, the drag coefficient is given as 1,700 over Reynolds number. Okay. So the same, the Reynolds number can be computed using this equation. Okay. If a flat plate or circular disc is placed normal to the flow, the total drag will contain negligible frictional drag does not change with Reynolds number or NR. Okay. By the way, what is Reynolds number? Okay. So the Reynolds number in our fluid mechanics, okay, the Reynolds number, it is a number which will help us to predict the flow patterns in different fluid flow situations, right? So for example, the Reynolds number of this particular fluid flow is equal to this, and then we can say that, okay, this is laminar, okay, this is just a basic flow, okay. And the low Reynolds numbers, flow tends to be dominated by laminar flow, while at the high Reynolds number, the flows tend to be turbulent. Okay, so turbulent flow, if it has a high Reynolds number, okay, in our fluid mechanics, we learned that the high Reynolds number means or implies that the fluid flow is turbulent, okay. And the low one, we have learned that it is a laminar flow. And then how to get the fluid Reynolds number in a Newtonian equation. So the Reynolds number, as I have mentioned from the previous slide, RE or Reynolds number is the same with the NR or Reynolds number still. Okay, so as I have mentioned, okay, we can see, okay, so it's still a viscosity. As I have mentioned, the viscosity or the mu is the fluid dynamic viscosity of the materials in kilogram per meter second. Okay, sometimes it is given in the formula, given in the problems, what is the specific viscosity of that particular product, particular flow. And then the density of the fluid, it might be air, it might be pure water or processed or mixed water. So it depends on the uh, problem or depends on the situation. And then we also have velocity. Okay, so when you say fluid velocity, it's the velocity of the fluid that being applied. So for example, in the processing, so the processed oil will be transported going to packaging. So that particular fluid flow will be measured. Okay, and the pipe diameter, what is the diameter of the pipe where the fluid flow is occurred? Okay, okay, so that's how we compute the Reynolds number. So actually, this is just a recap because I believe that you are done with this during your fluid mechanics, or maybe you are taking fluid mechanics by this semester, concurrent for this course, or this might be a review in your physics class. Okay, so as again, Reynolds number is used on predicting or knowing the type of flow or the level of flow of the particular fluid. Okay, so the higher Reynolds number, it means it's turbulence, but in lower means laminar. Okay, so consider a sphere object, for example, at a very low Reynolds number, less than zero point 0.2, Stokes law is applicable. So Stokes is another consideration which still covers fluid flow. Okay, so you review Stokes law, and then the Stokes law is also related to the flow of fluids, which is considering also the viscosity and specific gravity, I guess, of the fluid, particular fluid. So this law uh, simplifies or denotes that the inertia forces may be neglected and those of viscosity alone considered. So this is simple when you get uh, the CD value of the particular flow. Okay, so the CD value is just given as 24 divided by the Reynolds number. So this is this is also easier, okay, when getting the value of CD or the drag coefficient. So when once you know already the Reynolds number, and then it has a lower value, you can apply the Stokes law. Okay, Stokes law. Okay, for example, determine the drag coefficient of a 5 kilogram jackfruit. For example, there is a jackfruit falling from the tree to the ground with a projected area of 0.33 m square and a terminal velocity of 60 meters per second. Assumed density of air is 1.207 kilogram per cubic meter. Determine the drag coefficient. So when we say drag coefficient, CD, for a jackfruit that is falling down from the tree. So, sir, why we use drag coefficient, wherein this is not a fluid flow? Okay, there's still drag coefficient or a frictional coefficient for a material going uh, moving down or moving up. Okay, as long as it will have as long as the air will have a contributing factor for its movement. Okay, for example, pag mahulog tong jackfruit or any fruit ikan sa taas, di ba, pag mahulog na siya, ang factor nga makapahinay or makapaspas sa iyang paghulog are two factors: its own weight and the surrounding or the air of that particular surroundings. Mo nang pag mahulog, for example, ang lubi, matingala ka nga ang straight ang lubi na ara didto kay bawog ang iyang punuan, pero natingala ka nga nahulog sa imong ulo nga layo ra ka because of the factor nga na-attribute tungod sa hangin. Okay, so that's the concept. Again, for example, na lubi nahulog gikan sa taas, kabalo ka nga hiwi ang lubi. Okay, ang punuan sa lubi hiwi. So nag-assume ka nga dili siya mahulog sa imong ulo kay layo ra ka. You are, for example, 3 meters away from the kanang trunk or from the punuan sa lubi. Assuming nga wala, you already assume nga dili na mahulog sa ako. But because of the movement of the air, no, nga available sa environment or sa surrounding, nga naka-affect siya sa movement sa lubi, pagkahulog sa lubi, maotoy nakapamove sa lubi nga nipadulong sa imong ulo. So that's the drag coefficient. That's the essence of the drag coefficient. So drag coefficient is not just applicable for fluid flow, but also for the uh, objects na maapektuhan sa air. Okay, so that's the concept behind. So how to solve, by the way? For example, jackfruit. Okay, sir, wala na lagi gi-mention diha pila ang height sa jackfruit. So wala na. Okay, wala na gi-mention ang height sa jackfruit tree kay dili naman siya isa ka factor. Ang factor naman gid is its own weight and the density of the air, particularly. Okay, ang air naman gid ang weight. So how to solve? You get first the terminal velocity for a falling object using the drag, which is equal to its weight, right? So the the weight of the material is 5 kilogram, or the weight of the sample or the body of the jackfruit, so 5 kilograms, no? So its mass times the gravitational force, which is 9.81 kilogram meter per second square, which is equated or equal to what? The kinetic energy and its velocity for the falling terminal velocity. So you can have, what is this? The CD is equal to 2 times the mass times the gravity. So murag ko ano ni siya, simplify, gibalhin lang. So si CD, kaning si C diri, okay? Gibalhin lang ni siya ang atong pangitaon kung pila. So maka-come up taging ani. So kani 2 times the mass times the gravitational force divided by the density of air. Okay? Kaya ato naman yung gibalhin si C. So mahimo na ni siyang, instead of 1/2, mahimo na ni siyang 2. Okay? So basic lang interpolations. Okay? So density divided by density times the area times the velocity square. And then, naman tayo nga na, and then makakuha na tayo value sa CD. So what's the value of CD? 0.068. So that's the value of coefficient of the drag coefficient. So mao ito ang value nga naka-tend, no? Naka-apekto sa movement ni jackfruit going down sa ground from the tip or from the top of the tree, or gikan asa gito siya nga party sa kahoy. Okay? So that's how we compute the drag coefficient. Terminal velocity, by the way, is a particle that the speed of the terminal velocity of a particle depends on the properties of both the fluid and the particle, no? So the concept pod ganina, pwede pod the speed of the terminal velocity of a material depends on the properties of the material and the fluid flow. The fluid. Okay? So air and the weight of the material. So mao na siya ang mga factors na itong i-consider. So same ra gyapon bisan pag fluid ang flow, like fluid yun nga tubig or whatever, no? So the Fg, or the force of gravity acting to make the particle settle downward through the fluid, for example, is the resisting pod, no? Like a certain body, no? Mahulog siya ang iyang weight, napoy mo resist, mo to siya ang kadtong resisting force. So sa kanipod sa fluid, pag flow sa material, ang katupang mo resist sa iya, mo oppose, mo pud tong gitawag nga Fg, no? Or gravitational force, no? Put particle and still fluid steady. For example, magbutang kag something material or particle in a still fluid steady, no, nga fluid. What will happen? So the speed at which particles settle depends on the particle properties. Unsa diin nga property or particle, unsay size kahaan na in terms of diameter, sa kay density ano niya, no? Example, ang imong gibutang is grains, no? Crushed nga material, grains. Ibutang nimo diha and then magdepende gid diha sa iyang diameter, no? Sukdo nimo na micrometer sa kay sukod ano niya, and its density, no? Accordingly, shape niya, and then other physical properties sa particles, mo na imong ipang-consider para mahibalaan nimo ang iyang speed sa particles when it moves or settles, no? So mo na siya ating pang-consider. And then ang properties pud sa fluid nga imong gigamit. For example, kadto nga grains, imo siyang ibutang sa juice, no? So the juice itself, it has a unique characteristics and properties, no? And then the grains nga imong gibutang sa juice, no? Or whatever, shall we say rice, grind or kanang gigaling nga rice, ibutang nimo sa juice. So ang rice mismo na siya ay kaugalingon nga properties, plus ang properties pag mo sa juice. So mao na to sila. So magdepende sa properties ni juice o properties ni rice ang pag-settle down ni grains padulong ni rice grain kung ginaling padulong sa juice. So mao na siya ang ipasabot diha sa speed or terminal velocity concept sa process or mixture. So mao na siya. So some students will do research and then okay, mag-design ko gingani nga machine para ani kay akong i-crush, and then without reviewing the properties of that particular material nga iyang i-process or iyang kanang designan og machine, no? Example, you are designing somewhat a machine nga para mo crush ani nga product, mo cut, and then wala lang nimo gi-consider ang properties ana, bisag ang physical properties man lang, and then you will not know if that machine is applicable or suitable for your product because you have not reviewed the physical properties of that product, chemical properties, no? Aero and hydrodynamic properties. So when you do research, particularly on your thesis, please consider the various properties of your sample or your commodity, because everything, every aspect of that particular commodity will be needed or required in assessing or evaluating the efficiency of that particular process or machine. Okay, so that's the concept. Okay, I don't need to discuss and then give a lot of problems just to say that just to check or just to know that we have discussed this topic. What I'm trying to share with you is how these topics are important in our profession, in our practice, and in our research, and in any other endeavors related to agricultural and biological products. No, so anyway, computations, solving problems are just easy as long as you know the basic theory behind that particular topic. Like this one, we don't need to present a lot of problem solvings here in. As long as we know the concept, okay, the drag force, what is drag force, what is Reynolds number, what is the fluid flow, how it affects the properties of the material. So that's the most important thing, guys. Okay? And then to continue, we have a general equation for terminal velocity, by the way. Okay? So the general equation for terminal velocity is the factor of the mass of that particular falling object, okay? Okay? And then the gravitational acceleration. So due to the gravity, okay, which is 9.81 meter per second square. So it is just like head loss. The factor of the head loss according to the projected area of the object. Okay, so with respect to the projected area of the object. So actually, the square root of 2 mg is just called the head, or some scientists or some technologists will use square root of 2 mg. Velocity is equals to square root of 2 mg is just like a head loss, or the specific head of that particular flow or that particular process. Okay, so in a way, a terminal velocity is given by this formula. So we are all aware what is density, what is area, how to get the area. If it's pi, and then the area is pi over 4d square, okay, or pi r square. So let us not forget, and then let us still remember the things, or the shape, the particular product in terms of its area, how to solve the area of a square, how to solve the area of the triangle, how to solve the area of the sphere. Okay, so let us not forget, because not all the materials applicable for fluid flow are always pipe. Okay, there are some materials used in fluid flow or even in water flow that are being that are used, that are considered like uh, in a different aspect, like irrigation and drainage. So we use like trapezoidal. So you cannot apply uh, diameter, or you cannot apply pipe formula for that fluid flow, because it's already trapezoidal, and then it's being made by concrete. No, so it depends on the fluid flow, and then it depends on the material that is used. So that's the most important things, aside from considering the physical aspects of the product. Okay, so again, the terminal velocity of the product is the terminal velocity of the product is a factor of its head loss through the area of that particular product, and then the coefficient of drag, or drag coefficient. So that's the thing that you need to remember. So assuming a spherical particle material, for example, spherical daw siya nga material with diameter dp, no? Example, let's say what is an example of for example, spherical, or like a circle. Okay, so orange. Okay, so ang orange, for example, the Fg, or gravitational force of orange, depends on the volume and its density, okay, of that particular product. So given by this formula, where Pf is the density of the fluid. Okay, why fluid is present in this? Say for instance, the oranges are being conveyed. The oranges are being transported in a processing plant, no? Sulod sila, limpyuhan sila, hugasan, pagawas with the presence of water. So ang katong mga factors nga nakapahugas sa oranges. So the designer of that particular machine, the technologist, already considered the effect of too big to the oranges. So that's how this uh, uh, scientific knowledge must be considered. Okay? So, ganina, ingon ko, we can test or we can identify the uh, type of flow, okay, if we know the Reynolds number. Okay? So if the in the case if the Reynolds number is less than 0.0001 until zero point 0.2 or 0.0001 to zero point 0.2, then the terminal velocity can be found or determined using this equation. Okay? If the Reynolds number is less than zero point 0.2 and then less than 500 or zero point 0.2 to uh, 500, the formula for getting the terminal velocity, I mean, in coefficient of drag or drag coefficient will be uh, applicable using this equation. Okay, so you just familiarize this equation. The most important thing is you know how to solve the Reynolds number, and then after that, what's the value of the Reynolds number, and then that type of flow. So you can use this CD. Okay, so the first thing you need to do is measure the terminal. I mean the Reynolds number, and then, for example, if the Reynolds number is 480, and then you can use this formula for getting the CD. Okay, if the Reynolds number is more than 500 but less than uh, 200,000, okay, then you can use this CD value, I mean CD formula, okay, to get the terminal velocity. Because in getting the terminal velocity, we have to go back again. The terminal velocity, CD is important. Okay, this one. Okay, that's why, unsa man na si sir, yaw-yaw man na siya ng mga Reynolds number. Because when we get, before we can get the terminal velocity, we need to know first the value of drag coefficient. And then before we can solve, I mean, before we will know the value of CD, we need to get also the Reynolds number. No? So, ang iyang giingon diri magdepende man sa materials, magdepende man sa iyang shape or etc. Then, magdepende sa flow. And then, the Reynolds number, velocity, makuha man nato ang Reynolds, I mean, ang CD, gamit ang Reynolds number. No? So, if the Reynolds number is like this value, within this range of this value, then you use this particular CD formula and so on. Okay, so that's the concept. Okay, for example, in a lab experiment for the hydrodynamic properties of spherical food materials, freshly harvested or ripe hinog na watermelons were examined. Okay, at the first stage, yun siya, at the first stage of the experiment, the force of gravity or Fg was determined. Gikalkyo sa una ang force of gravity sa watermelons. Each watermelon samples of similar diameter Fg in Fg in 10 inches, no? Ang iya ding diameter sa mga watermelons 10 inches. Gipamutang to mga watermelons placed in a container filled or half full, no? Ang katong container gisudlan og tubig, tunga sa tubig with cooking oil. I mean, cooking oil dili tubig, okay? For example, naay container gibutangan og tunga nga oil, and then gibutang dito ang watermelons, and then if the average daw of if the average Fg was computed at 12.62 newtons, what is the approximate density of the fresh samples of watermelons? What is the estimated force Fb exerted by each sample, no? Unsa ka atong force nga na generate sa body or sa watermelon, no? For example, gibutang tong watermelon dito isa-isa. The first watermelon gibutang dito sa container filled half full with oil, no? Assuming nga naanay value daw sa Fg, which is 12.62 Newton. And then the diameter of each watermelon is equal to 10 inches. Okay. Ang pangutana, pila kaha ang approximate density sa fresh sample. Sa pag-solve, okay, using the general equation, okay, naatay nga ni ganina, we have identified this, which is equal to 12.62 ang atong Fg, you know, or 12.62 Newton. Okay. And then the formula is pi over 6, which is given already in the previous slides. Then the density sa fluid, so we used oil in this particular experiment, right? Times the 9.80 or the gravitational force times 2.54. So what is 2.54? It is the diameter, okay? It is the diameter. In 10 inches, so i-convert nimo into meter, mahimo siyang 0.254 meter. Since, okay, 2.54 meter. Solving simultaneously, shift solve nimo ni, find the value of density of the particle or the density of watermelons, and then you can get 150 kilogram per cubic meter. Meaning, ang density idea is a watermelon using the oil as a reference is 150 kilogram per cubic meter. The next question is, when how to I mean what's the value of FB or the weight of the body? I mean force resulted to the weight of the body. So assuming a density of oil which is 950 kilogram per cubic meter, okay? So lahi ang density ha. Sir, nganong lahi na po 950 kilogram cubic meter diha. Lahi man tong density sa watermelon ug lahi pud ang density sa oil, for example, okay? So meaning sa isa ka cubic meter, no, sa isa ka cubic meter 150 kilogram lang ang watermelons. So sa ka cubic meter maybe like a box. So timbangon nimo ang watermelon nga sulod ana, so 150 kilogram lang. Okay? Sa oil, isa ka box, 1 cube, butangan nimo oil, o then 950 kilogram ang iyang density. So using the formula again, makuha nato ang value ni FB. Okay? Since we already know the value of oil, density of oil, which is 950, then the value of FB is equal to 80 kilogram Newton. So that's how easy and basic on how to compute the force gravity or gravitational force according, with respect to the density of the material or the food product that you applied. Another example, a copra processing plant in Butuan City, for example, is known for producing high-quality coconut oil in the entire Mindanao. In the production area of that particular plant, the copra mill, itong machine na mo uh, mo extract sa oil from coconut meat. Okay, there's a difference between coconut meat and the coconut kanang oil atong meat katong iyang yung unod, no. So ang iyang milling machine, no, is observed to have an average extracting rate of 60 liters per second flowing through a pipe of 200 mm diameter. Okay, so after extracting the oil from the meat sa copra, so i-transport to ni mill, no, gikan sa galingan padulong sa maybe for packaging na nga area, using a 20 mm 200 mm diameter nga pipe, no. So mo flow dito ang extracted oil sa pipe. If the dynamic viscosity and specific gravity of the coconut oil, no, gihatag na niya ang dynamic viscosity o specific gravity, which is 0.90 kilogram per meter second and 0.95 respectively. So meaning 0.9 kilogram meter per 0.9 kilogram per meter second ang viscosity, and then ang atong specific gravity is 0.95. And then the question is, we have to get the value of Reynolds number for that particular flow of oil, and then the drag coefficient for that particular flow of oil, and then the terminal velocity. Okay, so when we say terminal velocity, ang factor ani niya is ang coefficient of drag or drag coefficient, and then the Reynolds number. So solve using the equation. So ang Reynolds number, di ba, ingani ang atong equation, which is RE or equal to NR. So they are the same. So using the density times the velocity times the diameter over the viscosity. So given man ang viscosity, makuha na to si density ni oil. Okay? So ang specific gravity, yung saan di pagkuha, di ba ang specific gravity is density sa oil divided by density sa water. Meaning, ang density dahil sa oil is 950 kilogram since given man ang SG nga 0.95. Okay? So, and then atay diameter sa pipe nga 200 mm or 0.2 meter with velocity nga 60 liters per second equal to 0.06 m³ per second, magamit na nato siya para makuha nato si NR. Since the formula for NR is the density of the fluid times the velocity times the diameter divided by viscosity. So ang NR or Reynolds number is equal to 12.66. So asa siya nabilong ang 12.66? Unsay formula sa atong discuss ganina kadtong magdepende sa iyang Reynolds number sa pagkuha sa CD. So nabilong siya sa range nga 0.22500, no? Or 0.22499. Meaning, ang drag coefficient nga atong gamiton formula is the formula nga gi-discuss nato previously for that particular value of Reynolds number, which is 12.66. Belongs siya sa range between 0.2 to 499. Okay? So the formula, okay, using that particular formula specific for that range, makuha nato si CD which is equal to 3.52. Okay? Since na naman tayo NR value nga 12.66. And then ato lang na siyang i-substitute diha, then the value is 3.52. The last question, it is not applicable to measure the value of what is the thing that being asked. Compute for the terminal velocity. Okay. It is not applicable to measure the terminal velocity of this flow since the material is free flowing, no, and not falling on motion. So it is not applicable if the material is uh, free flowing. So terminal velocity is usually applicable if it is being in motion. Okay, so it is mentioned that it is being free flowing from the mill going to. But let's check some examples because some examples will still compute terminal velocity even if it's free flowing. But somehow terminal velocity will be computed if there's something that will act or will cause the movement of that particular product. For example, a blower, uh, hydraulic, or any force that will move the material from one place to another. But to be safe, even if it's not applicable or not, as long as the units are given, for example, there's already CD, there's already NR, and then the formula for terminal velocity is a factor of CD, NR, and then the specific gravity or whatever, and then you can compute to be safe. So that's it. That's all for the aero and hydrodynamic properties. It's very easy as long as we understand the basic knowledge or theory about aero and hydrodynamic properties. Whatever the problems may arise, that I mean needs to be solved, or during exams you are given problems, the most important thing is you need to identify all the factors so that when computing using the equation, as long as you already have the uh, NR, and then you need to find the CD, then you can compute uh, terminal velocity and whatever. Okay, so it's just a process, and then it's just understanding the basic. So no need to bother your mind in terms of the complexity of the problems. Okay, so that's it. That's all for the aero and hydrodynamic properties of uh, AB materials. So thank you, and please solve at your own pace. Please solve different problems, related problems to aero and hydrodynamic properties, so that during exams you will be guided. Okay, you will have more knowledge and background about aero and hydrodynamic properties. So the most important thing is just velocity, specific gravity, viscosity, weight of the material, gravitational force, head loss or frictional factor, and Reynolds number, as well as terminal velocity. So everything will follow as long as you know the basic or even the equation on how to substitute and how to interpolate, and even I mean even how to play with the formulas or equations. Okay, so thank you so much, and I hope that you have learned a lot from this topic. Okay, so I suggest that you continue learning, or you learn at your own, you review, and then you solve similar problems related to this particular topic. Okay, so thank you so much.